Hello and welcome to Basic Logic, an open introduction to philosophical logic. I'm Dr. Nicholas McGinnis. In this course, I'll cover the basics of formal logic in a philosophical context. And the great thing is we'll only be using open source materials, which means that you don't have to pay for an expensive textbook. You can just go online and download it yourself. Let's get started. I'll be doing this thing where I kind of awkwardly switch the slides over. In this online course, I'm going to be covering just the very basics of modern formal logic. I'm going to discuss some of the philosophical issues, some of the practical applications of these formal systems. And all the chapter references you see below are to an open source textbook called For All X, the Lorain County Remix. These slides will also be made available in a shared Google Docs folder if you want to follow at your own pace. Now, I printed out For All X, but you don't need to. You can just refer to the PDF. There's a number of excellent exercises in the textbook as well that I highly recommend you do. I'm going to be trying to divide this course into 7 fairly longish videos, covering the basic concepts of logic, moving on to sentential logic as a formal system, then quantificational logic, and concluding with a video on the basic meta-theoretical concepts here. Don't worry if you don't understand what this means, it'll all be explained in due time. If you're taking a philosophical logic in university right now, hopefully this video lecture series will help you. If you're taking a computer science course where you're learning about logic gates and binary numbers, this might also be useful to you. So let's get started right away with part 1, Introduction and Basic Concepts. I also just want to thank the people who worked on For All X as an open source textbook. The basic textbook was written by P.D. Magnus, and I'm going to be using the Lorain County remix. So thank you to all these people that worked very hard on this open source project. So, also, there are several practice exercises and assignments throughout these slides and this course, and the reason is pedagogical. In logic, new concepts build on previous concepts in a pretty systematic way. And because formal logic involves the development of specific techniques for handling logical systems, the practical work is crucial. This is not a class where you can sit down, hear the concepts, and master them. It's more of a practical course. It's a skills-based course. It's important that when we get to the exercises in these videos, you pause the video and try and complete them. Answers won't be provided in the videos, but in the Google Doc folder, I'll try to make sure they're available for you. So this is a philosophical logic course, but much of it will feel more like a discrete mathematics course than philosophy. And in fact, it's funny, because I failed this course myself in college 15, 20 years ago, and I've gone on to since teach it. And don't worry, I did eventually pass the course, and I've taken other courses in logic since. I was 18 years old, and I didn't really know what I was doing with my life. But my real mistake was to treat logic like my other classes. I thought if I did the readings, highlighted the important concepts, and studied a little bit before the exam, everything would just kind of come together. And when that failed, I assumed I was bad at anything that looked like math. So in hindsight, I was kind of operating under 2 false beliefs in my logic course. First, that logic is conceptual, that it's a matter of understanding some concepts. And 2, that ability to understand these concepts is kind of innate. It's fixed. Either you're good at math or you're bad at math. Both of these beliefs are false, and I think it's important why that they're false in order so we can move beyond them and be successful in a mathematical logic course, in a philosophical logic course. So what does it mean that logic, that I was approaching it as a purely conceptual discipline? Well, a lot of people think logic is a matter of grasping abstract logical concepts via reading and reflection. But this isn't really the case. Logic, as we're going to study, it involves a body of skills and techniques that have to be practiced. Right? You're not going to learn how to play piano by reading a book about pianos. You have to sit down and practice. And logic is going to be exactly like that. And you might say, well, some people are just inherently musical. Well, maybe. I think that's true at the very highest levels of human performance in almost any skill. It could be athletic, it could be intellectual. Innate endowment will play a role. Tall people will be better at basketball. But at every other level, not at peak human performance, I find that the relevant variables are actually effort, discipline, practice, opportunity, persistence. So I think, the most unmusical person could play an instrument really quite competently with just a few months of practice. And this will place them well above the skills of 90% of the population who in fact don't play at all. They'll just consider you really musical. And getting into that last 10%, playing world-class music, well, that's the really tough part. But hardly anyone gets to do that. So don't worry about the people that are inherently musical or inherently good at these things. Don't compare yourself to genius. Persistence, effort, grit, dedication, those are the variables that are under your control, and those are the variables that are going to matter in a mathematical course, in a philosophical course such as this one. So if you're turned off by the amount of mathy-looking things in this class, don't worry. It just takes a bit of practice. And which kind of leads me naturally to the second false belief, which was my belief that ability in a specific domain, such as something abstract, something more mathematical, something more logical, is innate and it's fixed. But there's a lot of empirical evidence here that this isn't true. It turns out neuroplasticity, which is the ability of your mind to adapt to new information and get better at specific tasks, continues well into adulthood. The main cause of lack of ability in most domains is lack of practice. Right? Try throwing a ball with your non-dominant hand. I mean, you'll be terrible at it, unless you practice for a few weeks. Right? I'm left-handed. This feels really unnatural. But if I worked on it for a few weeks, I'd probably become ambidextrous. So the myth of innate ability is a bit of a self-fulfilling prophecy. We remain incompetent at things that feel difficult because we don't practice them. And we work on things that feel easy to begin with. So we create these feedback loops that seem to justify our belief that we are good innately at certain things and bad at others. But we practice what feels easier and neglect what feels hard. I know this feels like not logic, but it's really important because every time I teach this class, I have a lot of students who, after the first few lectures, want to drop the class, and they approach me and they ask, is this actually possible? Can I do this? Can I do a logic class? And my answer is always yes. But your study habits might have to change, and you're just going to have to practice a little bit. So, and I always point to the research of a psychologist called Carol Dweck. Now, she found that if you praise experimental subjects for their innate ability, for their intelligence, after any complex cognitive task, that will actually lead to depressed performance on subsequent difficult tasks. See, subjects praised for smarts deal poorly with their setbacks, because if they view intelligence as this innate trait that can be modified, any difficulty is just proof that you can't cut it on your natural talents. However, she also praised subjects for effort. And those kids felt they had a variable they can control, how hard they worked. And Dweck's studies demonstrated that they could bounce back from difficult assignments more than people who were praised for their innate intelligence. So here's a great synopsis from an article in the New Yorker back in 2007. And it's a great long read. Look it up. It's definitely worth reading. So Dweck sent 4 research assistants into a New York 5th grade classroom. The researchers would take a single child out of the classroom for a nonverbal IQ test, a series of puzzles, easy enough that all the children would do fairly well. Once the child finished the test, the researchers told each student his score and give them a single line of praise, and they were randomly divided into groups. Now, some were praised for their intelligence. They were told, you must be smart at this. Other students were praised for their effort. You must have worked really hard. Now, why just a single line of praise? This is still from the New Yorker. We wanted to see how sensitive children were, Dweck explained. We had a hunch that one line might be enough to see an effect. Then the students were given a choice of test for the second round, right? One choice was a test that was more difficult, but the researchers told the kids they'd learn a lot from just trying. But the other choice was an easy test, more like the first one. Now, here's the interesting part. Of those kids that were praised for effort, a single line saying you worked really hard, 90% chose the harder set of puzzles. But those praised for their intelligence, a majority chose the easier test. The smart kids took the cop-out. In the third and final round, none of the 5th graders had a choice. It was difficult, designed for kids 2 years ahead of their grade level. And everyone failed. But the 2 groups of children, divided at random, responded differently. Right? Those praised for their effort on the first test just assumed they hadn't focused enough. Dweck says, Look, they got very involved. They were willing to try different solutions. Many of them remarked, "This is my favorite test. This is awesome. It's so challenging." But not for the kids praised for their smarts. They assumed that their failure was evidence they weren't really smart at all. Dweck says, I was just watching them. You could see the strain. They were sweating. They were miserable. So if you were praised for being smart, what you feel is you have an intelligence score, like a D&D score, and that's fixed, and if it's insufficiently high, there's nothing you can do about it. But that's false. If, on the other hand, you feel you have a variable you can control, practice, effort, then failure is not a setback. Failure is a learning opportunity. And the whole point of this 10-minute byway, this tangent, is that as you approach a formal logic course, a philosophical course where you're used to reading, where you're used to being in the humanities, where we're reading essays, where we're developing our thesis statement, paragraphs, and now you're doing a class that looks like math, don't tell yourself, oh, I'm just bad at this innately. Say, well, I might need a little bit of practice to get it. That would be the right attitude to adopt. And in fact, this kind of myth of innate ability, I think, is pervasive, it's harmful. There is such a thing as innate ability, but it's only one part of a much more complicated cognitive whole, right? The variables relevant to actual success in a difficult task are under your control. The brain is more like a muscle that can develop as it works. So read the work of Carol Dweck, Google it, it's fascinating. Angela Duckworth has also worked on this. I think she calls it grit, right? The ability to persist in difficult situations. And if you have trouble in this course, as we go along, I'm going to do everything I can to help you translate your effort and your practice into success. So I don't know if you can read it on the board over here, but I have my email address here. So if you're having difficulty in the course, send me an email. No problem. I'd love to help. So one practice exercise I do when I teach the class is that at this point I stop and I ask people to answer some questions about neuroplasticity in Dweck's research. This helps you stop, think, and integrate this knowledge and remember it better than if I just had talked at you. So if you want, why don't you stop the video right here, press pause, and answer these 3 questions. How would you present this research to high school students? You might Google Dweck's work, make a couple slides. What's an example of an ability that is typically viewed as innate, something you either have or you don't? And what kind of exercise, practice assignment would you use to illustrate these concepts in light of your example chosen in 2? That'd be a nice way of stopping and thinking about Dweck's research on neuroplasticity. So if you want to go ahead and pause the video. And we're back. That's awkward. Well, I'm not going to start this whole sequence again. Let's just go to the next slide. All right. What is logic? 13 minutes into the video, I said I wasn't going to do this, but I did it. So the common use of logic in everyday talk is not what we're going to mean in a philosophical logic course. On TV, in everyday conversation, on internet forums, logic is used to mean any kind of moderately abstract reasoning. It could be deductive, it could be inductive, it can refer to science or to just common sense. So we see this sense of logic in tropes like tropes, which is familiar character traits and storylines. In the Straw Vulcan, that's a TV tropes link. You could just Google Straw Vulcan. And the idea is that we have an emotionless character like a Vulcan, like Mr. Spock, who is hyper-logical but can't solve like a basic problem because it involves some other aspect of humanity, like emotional intelligence. But the hyper-logical Vulcan is not exactly what we mean by logic either. Logic is a very, very specific subdiscipline, and I'm going to give you a definition in just a couple slides. But I just want to make sure you understand that separation here, right? Theory means something specific in a scientific context, as opposed to an ordinary context, right? And it's going to be the same thing for logic. If I say theory of evolution versus that's an interesting theory, I'm using theory in 2 different senses. And for us, logic will mean something really, really specific. We're interested in deductive reasoning, forms of deductive reasoning that produce valid arguments. And what is an argument? A set of premises that support a specific conclusion. And they support it in a specific way. Deductive reasoning guarantees the truth of the conclusion if the premises are themselves true. Now, we think of logic often as something maybe Spock or Sherlock Holmes does, right? But that's more inductive. When Holmes says he does deduction, he's actually doing something more like inductive, right? He's looking at patterns and regularities in the world and kind of making leaps of inferences that enable him to realize things that are likely to be true given what he's found already, right? He sees the dirty one side clean ring there, and he assumes that somebody's taking it on an awful lot, so maybe the husband's cheating. But that's not deduction. That's not logic in our sense. That's more like induction, more like scientific investigation. And that's not going to be our focus here. Logical deduction is reasoning on the basis of an accepted set of premises to reach a logically guaranteed conclusion that if the premises are true, the conclusion is necessarily true. Scientific induction, as opposed to deduction, is reasoning on the basis of evidence, and that evidence will provide strong but not certain support for a conclusion. Inductive reasoning is more statistical. The evidence makes a conclusion probable, and you can even have a very good sense of how probable the conclusion is, but it's not going to be certain. A good example of inductive reasoning is polling. If I call 5,000 people and ask them about their political opinions, I might have a good sense of what a larger population set believes. But it's not going to be certain. Polling doesn't always work. But if I have a true random sample, I can be fairly confident that my polling sample represents the general population. But that's not logic. That's not deduction. That's statistical induction. And that is not going to be the focus of this course. It might be the focus of a critical thinking course, but not a logic course. So how do you use information to give you a guaranteed conclusion rather than a merely probable one? That's an excellent question. Because we're going to be thinking of logic, and this is a quote from For All X, as the ability to make inferences on the basis of evidence. Inferences with a special status. They're absolutely certain if the evidence is in fact true. So here's an example of what we mean by that. Suppose I say only the butler or the maid could have committed the murder, but the butler did not, therefore the maid did it. Well, we see that if it's true that if it was either the butler or the maid and it was not the butler, then it must be the maid, because the schema of reasoning is it's one or the other, but it's not the one, so it must be the other. Right? To dispute the conclusion here is to dispute the evidence itself. If I say it's either A or B, premise one, but it's not A, the only option left is B. So the conclusion is guaranteed if the premises are true. If you dispute the conclusion, you're disputing the premise itself. And that's kind of the schema here, where the conclusion is guaranteed on the basis of the truth of the premises, is the fundamental insight in deductive logic. We're going to be looking for every case where the truth of the premises guarantees the truth of the conclusion. And here, premises 1, 2, and the conclusion at line 3 is an argument, a connected set of statements comprised of evidence that establish a conclusion. In a good logical argument, in a valid argument, if the premises are true, the conclusion is also certainly true. So, logic is concerned with making inferences on the basis of evidence. But the inferences are certain, provided the evidence is in fact true. That's the special... Did the lights just go out? I'll be right back. I guess I wasn't moving enough. The inferences made are absolutely certain, provided the evidence is true. I might have to move more so the lights don't go off again. We're going to call this evidence premises. And what's inferred from the premises is the conclusion. A set of premises establishing a conclusion is an argument. And a good argument, the technical term is valid, is one where the truth of the premises guarantees the truth of the conclusion. All right, this is a good place to maybe pause again, stop again. We're at 20 minutes. All right, we're back. Central to logic is this notion of an argument. And arguments have structure. And the structure is separate from its content. Logic is concerned with the forms of reasoning that are good or valid, as opposed to the ones that are bad or invalid. The book calls this content neutrality, and that's a good concept, because it really speaks to this notion in logic that it's not about the content of an argument, it's about the structure of the argument itself. So let's think again about this butler and maid argument. What is it really saying? Either the butler or the maid did it. But the butler didn't, therefore must be the maid. The general structure is either A or B, not A, therefore B. And it doesn't matter really what A and B are. Either the butler or the maid did it, not the butler, therefore the maid. Either the groundskeeper or the husband did it. It wasn't the groundskeeper, therefore the husband. Right? It doesn't matter what you put in. The structure of the argument is a good structure. Let's consider this argument here. All whales are mammals. Mr. Splashy Pants is a whale. Therefore, Mr. Splashy Pants is a mammal. It's pretty easy to see that the above argument is a good argument. Why? If every whale is a mammal, and Mr. Splashy Pants is a whale, we've already established all whales are mammals, Mr. Splashy Pants, being a whale, must also be a mammal. Right? You could kind of make a little Venn diagram where we see how these things work. But however, is this next one a good argument? All pigs can fly. Babe is a pig. Therefore, babe can fly. Is that a good argument? Well, in one sense, you might think it's bad because pigs don't, in fact, fly. But it's also a good argument in one logical sense, because if the premises were true, the conclusion would follow. It just happens that premises aren't, in fact, true. So to really understand logic, we have to make this distinction between validity, which is what we're interested in, what makes arguments good in logic, versus something else called soundness. Soundness is whether or not the premises are in fact true of the world. But to establish that, we have to kind of go beyond logic. We have to... This light thing is going to drive me crazy. Between validity and soundness. Sound is whether the premises are in fact true in the world. You might have to go and empirically investigate that. So the all pigs fly argument is valid, but it's not sound. It's valid because it has a form such that if the premises were true, yeah, the conclusion would follow. If all pigs could fly, and Babe is a pig, then Babe being a pig and all pigs could fly, Babe himself could fly. But it's not sound because the content is in fact false. Pigs don't fly. So logic is primarily concerned with content-neutral validity, with, in general, those forms of reasoning such that true premises would lead to false conclusions, no matter what we substitute in them. It could be about pigs or whales or butlers. It doesn't matter what you fill in the blanks with. The schema, the form, is what's important in logic. So, an argument is valid. This is probably the most important concept in all of philosophical logic. An argument is valid if and only if it's not possible for the premises to be true and the conclusion false. An argument is sound if and only if it is valid and the premises are in fact true. Now, validity, deductive validity in logic is always about the form of an argument. Soundness is about the content. Validity is content neutral. Now, to represent this idea of content neutrality, we're going to replace the actual content, the what an argument's about, with something more abstract. We're going to just use letters, which are going to stand in for variables, like in math. This highlights the form of the argument. Now let's look at these two. What we have here is either A or B is true. Premise 2, A is not true, therefore B is true. Right? That's our butler or maid argument. The other one, all A's are B's. C is an A, therefore C is a B. And these two argument forms are valid. No matter what we replace our letters here, A, B, C, we'll end up with a valid argument. They may or may not be sound. But we're not interested in soundness primarily. We're interested in deductive validity. So here's a practice exercise. Can we figure out together how to make the following valid arguments content neutral? That is, we take the content, what the argument's about, and replace that with variables. Keeping, however, the logical structure. So there are logical words in here. We're going to keep those. We're going to replace the about of the argument with variables. So here's an example. If Steve Rogers is right, the Avengers should not sign the Sokovia Accords. Steve Rogers is always right. The Avengers should not sign the Sokovia Accords. Either The Empire Strikes Back is the best movie ever, or A New Hope is. If it's Empire, then a Star Wars movie is the best ever. If it's A New Hope, then a Star Wars movie is the best ever. The best movie ever is a Star Wars movie. So why don't we pause the video, work on these examples a little bit, and come back. All right, so let's talk about these two arguments since we paused the video. Well, I'll be right back. That's me, by the way. All right, so the argument was, what was the argument? If Steve Rogers is right, then the Avengers should not sign the Sokovia Accords. Steve Rogers is right. The Avengers should not sign the Sokovia Accords. So, how's this going to look? It's going to be pretty straightforward. If Steve Rogers is right, which we're going to represent by R, then what? The Avengers should not sign the Sokovia Accords. If R, then S. But R is definitely the case. Steve Rogers is always right. Not Tony Stark. It's like an alcoholic. So, if R, then S, R, therefore what? The Avengers should not sign the Sokovia Accords. You can tell I wrote these slides a few years ago, back when Civil War was a thing. Yeah. How about that Infinity War, though? So that's a pretty straightforward argument, right? If R, then S. So if R is true, then S will follow. R is the case. Therefore, S will follow. And with this argument schema, you can replace it with almost anything you like. If I'm teaching this class, then I'm on YouTube. I am teaching this class, so it's on YouTube. At least that's the plan. I haven't actually uploaded it yet. So I'm talking right now. Okay, what about this other more complicated argument? Our second example. So let's look at it again. Either The Empire Strikes Back is the best movie ever, or A New Hope is. If it's Empire, then Star Wars is the best. If it's A New Hope, then a Star Wars movie is the best. So the best movie ever must be a Star Wars movie. So, either, premise one, Empire is the best, or A New Hope is the best. So E for Empire, H for A New Hope. So either E or H. Premise two, if it's an let me just put my if here, if Empire is the best movie, then a Star Wars movie is the best ever. Slightly more complicated argument. If it's A New Hope, then same conclusion, a Star Wars movie is the best ever. Conclusion, a Star Wars movie is the best ever. That's how we would strip away the content of the argument and then keep the logical vocabulary, the ifs, the thens, the or, and remove every reference to what it's about, the subjects, the topics, with variables instead. So either E or H. So one or the other of this, we can kind of informally see why it's a valid argument. Later on, in probably video 2 or 3, I'm going to actually give you a proof system for demonstrating that it's valid, but let's just kind of reason our way informally. It's either one or the other. If it's one way, then S is true. If it's the other way, then also S is true. So either way, S will be true. Now, to dispute the conclusion is to dispute one of the premises. Because premise one says, these are the only two options on the table. One of these has to be true. Actually, the or and logic, both of them can be true. We're going to get to that. One of these has to be true. If one is true, then S. If the other is true, also S. So no matter what, if the premises are true, S is going to be true as well. So, Now we can do the reverse and change the variables here into a specific content. Is the resulting argument sound? So why don't we pause the video, you work on that practice assignment, and I'll be right back and we'll work on them together. Okay, let's do it. Did you pause? You didn't, did you? Sorry, I'm trying to be funny, but it's actually weird in an empty classroom. Usually there's like a vibe, the energy of the other students, but now I'm just talking to no one. It's weird, man. Okay, so let's look at these arguments. I'm just going to write them on the board, and then I'll bring back the webcam. So we have all A's or B's? C is an A, therefore C is B. If you just think about it this way, it's actually kind of hard to determine whether or not the argument is valid. I hope you can read my handwriting. The lighting is kind of bad. So all A's are B's. So how can we substitute that? Why don't we just go back to whales and mammals, because that's a fairly easy one to understand, right? So all A's are B's. So we're going to replace every instance of A, all whales are what? Mammals. Now, the variable always will represent the same thing throughout the argument. So the B that was here and the B that was there will have to be replaced with the same thing. All whales are mammals. C is a whale. C is a mammal. Who's going to be C? I don't know. Let's go back to Mr. Splashy Pants. So we're going to replace it again. All whales are mammals. Mr. Splashy Pants is a whale. Mr. Splashy Pants is a mammal. Valid argument. Now we'll do it again for the other example. Right? Either A or B is true. A or B. I'm sorry, I just sneezed. A is not true, therefore B is true. So it is not the case that A, therefore B. All right, this one's easy. Either Star Wars or the Marvel Cinematic Universe is the best franchise, but it's not Star Wars, therefore the Marvel Cinematic Universe is the best film franchise. Now, this was disputable. Then the prequels happened. So, this is the kind of thing we're going to be doing. A critical thinking class would focus on argument in a more broad way. It would include rhetoric, statistics, induction. It would talk about logical fallacies like ad hominem, slippery slope, to quote Gary. It would talk about our cognitive biases, different techniques of persuasion. A critical thinking course is really about argument in the wild. But formal logic, the kind of thing we've just been doing, is more of a laboratory of argument. Right? We're going to be dissecting arguments, placing them in these really artificial conditions that are not going to resemble the real world very much. By doing this, we're going to hope to discover very general features of logic, but in terms of having real world applications, is this going to make you better at arguing online or convincing your parents that you're right about something? Not necessarily. Formal logic is kind of its own thing. It might help. It'll definitely help with things like programming. But will it make you a more logical thinker? Well, I'm not sure. But formal logic, I think, is still interesting and worth studying in itself. But what we're going to be generally doing in this class is abstracting from specific arguments and looking at their formal structure. So, to quote, for all X, right, formal logic takes arguments out of their natural habitat, performs experiments on them to see what they're capable of. They're kind of like lab mice. They live lives that are very different from the wild cousins. And this will tell us a lot about the limits of logic as a process. But we're not going to do a lot of things like reading the editorial page of a newspaper to find the logical structure of the arguments there. Formal logic is a lot more abstract than that. at least the way we're going to do it. So, now, YouTube always says that these long videos are going to be unwatchable. So maybe I'll stop here at 1.2, and I'm going to start a next video in this series for section 1.2, because 35 minutes is pretty long. Thanks for watching. The next video in the series is coming right up.